This is group 23, and it's our video solution for a statically indeterminate beam. My name is Deborah Dumas, and I'll be starting off the problem. So we'll just go through what the beam looks like. So what we have is a beam with a fixed support at A, and going to the right we have a load P midspan, then we have a pin at support B. So what we're asked to do is compute the reaction at A in terms of B, plot the curvature diagram, and finally use the moment area method to find the reaction at B. So we'll start off with the free body diagram. First, we know at a fixed support we'll have a reaction in the Y, a reaction in the X, and also a moment at A, which we assume to be clockwise. Going to the right, we have a force again at P, and we have a force going downward at B. Now, we assume this to be going downward, and I'll explain in the next step why we assume it to be going downward. So what we're trying to do is find a reaction at By, but this is a statically indeterminate beam, so technically we can't use the moment area method. So what we're gonna do is assume that By is like a known force. But we know that the deflection at B, because of the pin, is going to be 0. So after we solve for a deflection, we'll set it equal to 0. And this would be our deflection diagram if B had a force going down. So we'll solve for the reactions at A. The sum of the forces in the Y is equal to 0. So we have AY, and we assumed it to be going up, minus P minus BY equals 0. Solving for AY, we get AY equals P plus BY. Then, to solve for the moment at A, we take the sum of the moments, counterclockwise being positive, at 0. We set it equal to 0. So we have P times L over 2, it's moment arm, and that's a positive moment, minus P plus By, which is just the force at A, times L, and that's a negative moment going clockwise, minus the moment at A, which we assume to be negative. And solving for the moment at A, we get negative PL over 2 minus By times L. Now we're going to move on to the moment and shear diagram.
My name is Brandon Edwards, and I'm going to be talking about the shear and moment diagrams. First, we have the free body diagram again, and as found earlier, we found the forces in the A, the moment at A, and then we said we had a given force of By. From there, we have all the information we need to find the shear diagram, and we said that AY was P plus By, so there's your first force going up, P plus By. Your next force is the force of P, so as you come over across, you have P plus By minus the P, so then your next point is just By. And then your last force is just your By coming down, ending at 0. And then again, from there, you have all the information you need to do the moment diagram. And we found, again, the moment of A is starting in the negative direction, and it's negative of the quantity PL over 2 plus BYL. So that's your first point, and you start there. And then you know that your next critical point is going to be the area of this rectangle right here, which is the point BYL times distance of L over 2. So your next point's, and then negative BYL over 2. So you have all your known critical points to find the areas associated with each of them. From there, we broke it up into 3 areas, area of these 2 triangles and the area of this rectangle right here. So first off, we have the area of this triangle, and it's 1/2 base times height, base, and then obviously the height is that critical point. And from there you get BYL squared over 8, and I didn't write out the EI for all of them, but you have to carry the EI over since it's M over EI diagram. And then for area 2 is just the rectangle, so base times height, that comes out to negative BYL squared all over 4 EI. And then the only somewhat tricky part is you need to find the area of this triangle, but the height of that triangle is the height of the moment minus the height here. So that's what this is. It's the negative PL over 2 minus BYL, which is your moment height. and then subtracting of the height of that other triangle, BYL over 2, minus the negative. So what you come out with is the height of that triangle is negative PL over 2 minus BYL over 2. And then what your final quantity comes out to, because you have to multiply it by the L over 4, which was just carried over from here. So your final area is negative PL squared over 8 minus BYL squared over 8. And the last thing we have down here is the deflected shape diagram, shape diagram. And we have the forces written in here. And you just need to know that since A is a fixed point, there's not going to be any slope there. But B, the pin, will have a slope. So we show the theta B.
My name is Jeffrey Fry, and I'm going over the last part of our problem. After we have the moment over EI areas for these different sections, then in order to put them into the moment area formula, we're going to want to multiply those areas by the centroids. The areas for these sections we got last time, these are all written up here. Putting them into the moment area formula, we multiply them by the centroids, and that's the following here. 2/3 L over 2 is the centroid for A1, which is 2/3 this distance. The centroid for A2 is here, which is going to be halfway over this next L2 area. So that gives us a 3/4 L. And the centroid for A3 is going to be 2/3 past this area here, and that's L2 plus 2/3 L over 2. Then we can put in the areas that we had above into here for the A1s, the A2s, and A3s, which are the areas that we got. And that's just writing this down into here, and we also simplified the centroids at this point. So that gives us this equation, which is A1 times the simplified centroid, A2 simplified centroid, and A3 times the simplified centroid again. These next two parts are just the simplified part of that, where this goes down and we put that together, put this together here, and these together here. After that, we simplified it further by pulling out a common denominator of 1 over 48 EI, and these coming back down gives us all of these in the center here. Finally, after that, we combined our terms inside. The BY's all went together to make negative 16 BYL cubed, and the negative 5 PL cubed just came down on its own here. At this point, we can solve for the reaction at B, because we know the actual displacement at B is 0 since it's at a pin. So setting it equal to 0 allows us to find what the force of BY will actually be in terms of P. So at this point, we move this side of the equation over here. Our 1 over 48 EI cancels out with a 0. And this turns into 16 BYL cubed is equal to negative 5 PL cubed. And that gives us a final solution of the force of BY is equal to negative 5P over 16. This solution makes sense because our BY will actually be facing up since the force P is coming down. And it should be about half since it's in the middle, but there's some of it that's taken away by the moment at A. And that means that this final solution makes sense. To recap, what we did was we put everything into the form of a reaction at A. We took that to find the moment areas for all of these, and put that into the moment area equation times the centroid to find what the displacement at B would have been. Setting that displacement to 0, we got our final solution of BY is equal to negative 5P over 16. And that concludes our problem.